All right, I don't want to wait any longer. Let's go ahead and get started. And so my name is Brian Ekins, and I'm the designer for the Fusion API. And today we're going to go over how geometry is represented in Fusion. And personally, this is one of my favorite areas. I think this can be kind of fun, some of the stuff you can do. So here's just some of the stuff I wanted to talk about is, so how is geometry represented? And looks like the update is really slow here, but I'll kind of keep going and talk through. And so how is geometry represented? How do you get to the geometry that's in a Fusion model? And then what about sketches? What about surfaces? What about solids? What about T-Splines? What about assemblies? Does that change anything? And then how do you create and edit and query, I guess. So we'll talk about all of that stuff. So first, we'll look at how a solid is represented inside Fusion. So what is a solid? And a solid isn't really solid. So solids are represented in Fusion using what's called a BREP, or boundary representation. And where that term comes from is a solid is really made up of a bunch of connected surfaces. And if it's solid, those surfaces connect and it's watertight, so it defines a volume. And so that's a solid. And because it's a tight, watertight, enclosed volume, and Fusion knows which side is the inside and which is the out, it can kind of make that behave as a solid. So when you do mass properties, you get mass properties for it as if it's a homogeneous piece of whatever material you've assigned to it. And when you do operations on it to cut and punch holes through it and things, it's actually intersecting and trimming surfaces, but it knows how to do that in a way that it looks and behaves like a solid. But the solid really is just this patch of surfaces. And in addition to just a bunch of surfaces that kind of touch, there is some additional information that actually defines how they're connected, and that's referred to as the topology. So with this BREP, we have the topology and we have the geometry. So the geometry kind of describes the shape, and the topology describes how everything is connected. So go through in a little more detail the API that exposes all of this information. And so the very top level thing is called a BREP body. So from the component, there's a collection of bodies. So this BREP bodies collection. And then, of course, each body is represented by this BREP body. And so these are the same thing if you look in the browser and there's a bodies collection or a bodies folder that you can open up and see individual bodies. You can turn their names and all that kind of stuff. So those are these BREP body objects. So if I get a BREP body, I can get its name. I can change its name using this object. I can change whether it's visible or not. But what we're going to talk about here is how do I look at what's inside that body. And so we have the body, and then the next thing underneath that is something called a lump, or BREP lump. And this is something that's kind of standard. So this BREP idea is very common in the industry. So almost all of the solid modelers that you would use this same concept of this BREP, where the solid is defined by a set of surfaces. And the structure that Fusion has is kind of industry standard. And so the API is exposing really this full structure but it happens to be in this case that lumps aren't really used by Fusion. So what a lump is it's a group of surfaces like the body. So in this case, if I made that hole bigger and so it cut this piece into two, this could still be one body but two lumps. So it's two sets of connected surfaces, but they're still grouped together logically into a single body. But Fusion doesn't allow that. So if I actually did this operation that you see there, it would, so I had one body, I made that hole too big, and now Fusion would actually create a second body. So it never has a body with more than one lump. So in Fusion, it's always one-to-one. So lumps end up, at least today, and maybe it'll change in the future, but at least today they're not really used in Fusion since it's always one-to-one. The next thing down is something called a shell, and in the API we call it BREP shell. And these are also a set of connected surfaces, but so in this case with this box, so I've got two voids, so they don't connect outside, they're just hollow spaces within this box. And so each of these is a shell, because they are all part of the same lump and mainly the same body. So it's one body, but I've got these hollow spaces within the body, and each one of these is represented as a shell. And the BREP shell has a property on it called isVoid, and so that would tell me if isVoid is false, then I know I have this outer shell, and if void is true, then I know it's one of the inner two shells. So, but typically in almost all parts, well, in Fusion you're always going to have one lump per body, and you're almost always going to have one shell per body too. So having these voids aren't very common because you can't really manufacture it. I guess 3D printing you could, but it's not that common to have voids inside of parts. But you can have it. So the API supports that, so you can have these shells. Whoop. All right, and then so the next level down is from a shell. I can get the faces that make up that shell, and a face is each of the single surfaces that make up that body. And I don't know how this will paint for people. You'll probably kind of see it, but so this part that we're looking at now is made up of 7 individual faces, and each one of those, say, is represented by this BREP face object. And so a face is always just a face, so it doesn't matter what shape the model is. So that top face that we're looking at, it is a plane, but it's represented by a BREP face. And that cylinder hole that cuts through there, that's a BREP face too. It happens to be a cylinder, but it doesn't matter what the shape is, everything is represented by a BREP face. And there are shortcuts. So if you notice the little object model on the right, some extra lines came in. And so I don't have to go through lumps and shells if I don't really care about it. From the BREP body, I can ask it, give me all of the faces. And if there did happen to be multiple shells, that's okay. It will just give me all of the faces and all of the shells. But so this is probably the most common, is from BREP body. I would directly ask it, give me all of the faces, and now I can iterate over each of the faces that make up that body. And then we have loops. So from a face, I can ask it for its loops. And so let's isolate just that top face of the model. And what a loop is it's this boundary of the face. So this face has 2 loops. It has this outer loop, and it has this one inner loop. So all faces will have one and only one outer loop, and they'll have 0 to n inner loops. And the next thing we have is an edge. And so here's this edge highlighted here. So that represents the connection between faces. And so a loop is made up of multiple edges. So that's what a loop gives you, that set of edges that define the boundary of a face. And then each edge defines the connection between two faces. And an edge isn't unique for a face. So that edge that's highlighted, that's shared by that top face and that side face. Okay, so there's a single edge there that's shared by those two faces. And an edge, like a face, is always just an edge. So that edge happens to be, the geometry happens to be a line, but the edge that it's connected to it around the end of that part is an arc. And so an edge is an edge, but they can have different underlying geometry. And we'll look at that a little more in a second. And the same with a face, there's shortcuts to get to edges. So from a body, I could say, just give me all of the edges in this body. Or from a shell, give me all the edges. From a face, give me all of the edges. So there's different ways to get collections of edges. And then a vertex, so that's a little point at the end of an edge. And just the same as where an edge isn't specific to a face, but is shared, the same with a vertex. So a vertex is shared. In this case, these three edges that connect into that vertex, they all share, there's one vertex there that's shared between those three edges. And so that vertex is giving us some more of that topology of how things are connected. So I get the faces that tell me which two, or edges tell me which two faces connect to that edge, and a vertex tells me which edges connect into that vertex. And so I can query this structure that we're seeing on the right. I can kind of go up and down. So if maybe a user selected a vertex, then from that vertex I can ask it, okay, give me all of the edges that you're connecting. And so then I can get those edges, and I can ask those edges, okay, give me the faces that you connect. And then I get those two faces, and but I can also go down. So again, from a body, I could get all of the faces, and then on the face, I could ask it, okay, give me all of your edges. And on the edge, I could say, okay, give me the vertices that you can, that are your start and end. So I can use this topology information to traverse through this entire BREP structure. And vertices, again, I can shortcut that to get to them directly without having to go through this entire structure. And then there's one other concept that's not used that much, but I don't want to talk about it, is what's called a CoEdge. And in the API, a BREP CoEdge. And so again, if we isolate this one face, and what a CoEdge is it's kind of like an edge, but it's not defining connections to other things. It's defining the boundary of that surface, and this is unique for that surface. So CoEdges are unique per face. So the face owns those CoEdges. They're not shared by any other face. And because of that, CoEdges can have a logical flow. So CoEdges around a face, the outer loop, they go counterclockwise, and any inner loops, they go clockwise. And so and there's some cases where you can take advantage of these directions to do some computations, but these aren't commonly used, but just when you're looking through the API and you see a CoEdge, then kind of have a little bit of an idea what it is. Another thing that's a little strange about CoEdges is they're defined in 2D space. So if I got the line, one of those lines that we can see that would be a CoEdge, it that would be a 2D line, and the coordinates are defined in the 2D space of the surface, which I'll talk about some more in just a second. All right, so solids versus surfaces. So if I draw a rectangle and extrude it, using the solid extrude, then I have 6 faces, and the resulting volume is entirely enclosed. But if I do that same extrusion and I'm in the patch environment, then I end up with that picture we see there. So I just have the 4 faces around it. And so through the API, that same structure still applies. I have one body here, and it's made up of 4 surfaces, and I can interrogate those surfaces, and I'll just get a little bit slightly different information when I ask some of the faces. So for example, that top face, it still has 4 edges, but now 2 of those edges don't connect to any other face. So that's really the difference between a solid and a surface is I have some open edges that don't connect to other things. But as far as querying it, there's no difference. And there's a property on the BREP body called isSolid that tells me if it is entirely closed or not, or if there are some open edges in the body. So if I care if it's solid or not, I can do a quick check and see, and probably in most cases I don't really care because I can interrogate it just the same whether it's a surface or a solid. Another difference of solids versus surfaces is a normal. A normal is given any point on a face, it's a direction from that point that's perpendicular to the face, or we call it normal to the face at that location. And for a solid, if I do a normal calculation and get a normal from a solid, the normal always points out of the solid, away from the volume of the solid. But if it's a surface, there is no inside. So the direction of a normal is arbitrary, really. All right, so if you want to create BREP data, right, that's done by creating features, or I can import some data. I could import a step file, for example, and that'll create a big BREP chunk of data. So today, if I want to create any BREP data, it's only done through importing basically an existing defined BREP, or by using features to define my own shapes. And then editing is done by creating features, and possibly in the future, Inventor supports this through something called transient BREP, but possibly in the future you'll be able to kind of define your own BREP structure and create it directly. But it's something that's not commonly used, and it'll be quite a bit of work for us to do, so we'll wait and see if that becomes a demand or not. All right, T-Splines. So when you use the form feature and create some geometry, and so you can define these crazy, really organic shapes. And so T-Splines aren't currently supported by the API, although it's something we've begun the design on. But so it'll come in the future at some point, but currently it's not supported. But when you exit a form feature, the T-Splines are converted to just a regular BREP body. So once you've exited and then are just in the standard parametric environment, then that's just a standard BREP body that you can interrogate just as if it was created any other way. So even though T-Splines themselves aren't supported, the result of the T-Splines is supported. You can have complete access to querying those. And as I said, support for T-Splines is planned sometime in the future. Right. So in the API, there's a couple of terms that we try and use consistently all the time, and it may not be obvious unless you kind of know this, but the first term is an entity, and that's the definition of an entity is really anything that you can select. Okay, so I can just in the UI I can select a face. Of course, I can select a sketch line, a construction plane. So anything that's selectable, we call an entity. And then geometry is just the pure geometrical definition. So if so we looked at a picture earlier of that body that had some planar faces and it had the cylindrical face. And so if I ask a face, there's a property on a face called geometry, and if I call that, then I'll get back an object that defines that geometry. So for that top face, the plane, I would get back a plane object, and for the cylinder, I would get back a cylinder object, and so that defines the shape of the face. But so that the face is an entity, that's something I can select, and then the geometry is just a property of that face. And yeah, so here you can use that geometry property to get it. And when I get the geometry, that's one way to think of it. It's a snapshot of the current shape. So Fusion is looking at that face. It's getting information about it. It creates a plane object to give back to me. And now that plane, when I look at the information in that plane, it does accurately describe the current shape of that face, but they're independent now. It just looked at it, created the plane, and gave it to me. So now, if I edit that the plane object that I get back, nothing happens to the face. Or if I edit the face, nothing happens to that plane. It's not going to update to show me that the face has moved in space or anything. So it's a snapshot of the current state of the entity of whatever I got that from. And geometry is represented by these, we call them these transient geometry objects. So when I get that plane, the plane object is transient, meaning that you don't see it. It's not selectable. It's not saved anywhere. It's just this object that wraps the information that describes a plane or describes a cylinder or describes a sphere or different shapes. So they're these transient geometry objects. And as I said before, editing the geometry doesn't change the entity, and changing the entity doesn't affect the geometry because they're just this snapshot in time. And it's not displayed or saved. And you can create transient geometry yourself by using there's some static methods to create. So I could say create a line, but what I'm doing is I'm just creating kind of the definition of a line. It's transient, so I wouldn't see anything happen inside Fusion. There's nothing, I didn't create anything that's going to be displayed. It's not going to be saved. It's just this temporary description of a line. And where this is most commonly used is points. Right? So we've seen this in previous programs where I'm drawing a sketch shape. So if I'm going to draw a line, I define the two endpoints of that line using a transient point. So I create a point 3D object just by supplying the XYZ coordinates. And so that point 3D object doesn't represent a real point in Fusion. It's just a wrapper for the X, Y, and Z coordinates. And then I can pass that in to the add by 2 points sketch line object. So I pass two of those in, and now Fusion creates a real sketch line using those two coordinates. So here are the geometry objects that Fusion supports. So we've got these different surfaces. So there's the base class surface object, and then cone, cylinder, elliptical cone, elliptical cylinder, NURB surface, plane, sphere, and torus. So when I query a face, and on that face, I call the geometry property, I'll get back one of those objects. So all faces in Fusion are represented by any one of those shapes. And then the 3D wireframe, so I'm going to get back any one of these types, arc 3D, circle 3D, ellipse, and so on, whenever I query an edge. So if I ask the edge for its geometry, I'll get back one of these shapes. And so there's a couple in here. Well, one that maybe is a little bit interesting, this infinite line. And that's if I go to a construction line, or construction line, construction axis anyway, and ask it for its geometry, it's going to return an infinite line because it's not bounded on either end. And if I query a vertex for its geometry, I'll get a point 3D object back. 2D geometry isn't used very much in Fusion because sketches are all 3D. But where 2D is used is what I just talked about earlier, was those CoEdges. So when I get geometry from a CoEdge, it's going to return 2D geometry, and because it's defined in the space of the surface, which we'll talk about in a second. And these other ones that I have up here that aren't geometry, but they're just other transient objects that are used quite a bit when dealing with geometry. And there's these kind of math-related objects. So I can get the bounding box, so that returns the minimum and maximum points of a box. And typically that's used so I could ask a face, give me your bounding box, and that'll give me a box that encloses that face. So I kind of know the area in the model that's occupied by that face. And then I have matrix and vectors that I'm not going to go into much detail here today, but the API supports those. So these are utility objects that you can use. All right. So there's another object referred to as this surface evaluator, and I can get one of these from a face, or I can get it from geometry too. And this lets me do more advanced evaluation of surfaces. And so, for example, this is how I would ask Fusion to calculate normals and return normals from a surface, or to get tangents, or to get the area of a surface. And there's derivatives I can get back. So there's these more advanced kind of calculations that I can do on surfaces. It's done through this surface evaluator object. And you can get this from a face, or you can get it directly from geometry too. So let's say I have a well, that part that we saw earlier that had the hole cut through it, but on the front part of that it had kind of a partial cylinder, so it had that rounded front. And so if I got that face, that partial cylinder face, and then I get the evaluator from the face, the evaluator will take into account information it gets from the face. And so when I ask for normals from that face, they'll always point out of the solid. And it also takes into account the boundaries of that face. So it knows that there are two lines on the edge and two arcs on the top and bottom that define the limits of that face. And so it's able to take those into account. Where if I got the face and then I got the geometry from the face, it's going to return a cylinder because that face is cylindrical shaped. But now that's a full cylinder. It lost all the information about how the face had limited the shape of it, and it also lost the information from the solid. So now when I do queries using that cylinder, it's going to be different than queried when I got on the face, because now the normal, it doesn't know which direction to point the normal. Either one is valid, and it's not bounded anymore. It's an infinite cylinder. So it's best to get the surface evaluator from the face and do queries on that. This evaluator uses pretty heavily the parameter space of a surface, and I've been saying I'll talk about this more in, I think, the next slide, next one or two slides. But so it uses heavily the parameter space of a surface. And yeah, so first, let's talk about the different surfaces or different spaces that you'll see in Fusion. So the kind of the common one is just model space. So if I turn on the main construction geometry, and I'll see that little picture that you see there. So I see the origin, so 0, 0, 0, and I've got red, green, and blue, and representing the X, Y, and Z axes. So that's model space. And then there's sketch space. So if I have this block and I pick that kind of brown face that you see there that I want to create a sketch on, then Fusion creates this new sketch, and a sketch is 3D space reoriented within model space. So it's not the same as model space. It is 3D, but it's this 3D space oriented in model space. So when I create the sketch on that face, then this is what I see. So Fusion draws a plane on the XY plane, and so you can see there's a green line and a red line representing the X and Y axes of that face. So Fusion, somewhat arbitrarily, but it given the face that I picked, it created this 3D space for my sketch, and the XY plane of the sketch will lie on the face that I picked. And usually people just treat a sketch as 2D, so they're going to draw on that XY plane, but it's not limited to that. I can draw in 3D too, but when I draw geometry in that sketch, it's relative to sketch space. So you can see where the origin is with that little datum symbol. So that's the origin of my X space, and then I have the X and Y directions and then Z coming out. And so I can draw in that full 3D space. And then there's some functions on a sketch to let me kind of convert between that sketch space and model space. So I can get the transform, if you're familiar with that, from the sketch, or there's some other functions to just say, okay, here's a point in model space, now give me the equivalent point in sketch space, or vice versa, to go from sketch space to model space. All right, then there's a surface space, and that's what I was talking about before with that 2D geometry with the CoEdges are defined in this space, this 2D space, and I'll go into a little more detail on that. But how this is any surface, you can think of it as being made of rubber. And so first I have this rubber sheet, and I draw this grid pattern on it. And now I can take that sheet of rubber and stretch it into any shape, but I still have that grid pattern on it. So I could stretch it into some weird shape like you see on the screen, or I could just fold it up into a sphere, wrap it around so some ends touch, or into a cylinder, and then I could kind of squeeze the open ends closed, so then it's more like a sphere. And so I can stretch it around and move it into any shape that I want, but that grid still exists. And so I can specify any point on that face, any point on that surface, by two coordinates. Kind of an X and a Y coordinate on that grid defines any point on that surface, no matter what shape it's in. And so this is the 2D space of a surface. And then finally, there's kind of curve space, which is 1D. So it's just a single value that defines any point along this curve. All right, so a little more on parametric space. That one can be a little harder to understand, I think. And so what I've done, I've written a little sample to kind of illustrate this. I hope will help make the concept a little clearer. All right, so I've got a model here. Give it a second to update. So I've got several bodies here, and let's see. Right now, I'm going to turn most of them off, and because of the latency with the, I have to go kind of slow here. And so I've written a little add-in. And what different things is it'll draw that grid on the face. So what this does is, so it has me select a face, and then the program is getting that selection. It's getting the surface evaluator from that face, and then one of the things that surface evaluator does is it says, okay, give me the minimum. So we talked in that previous slide, the surface space, how we have this grid, but what is the minimum and maximum values of that grid? So it's not necessarily always 0 to 1, but usually it's something else. And so I can ask, when I get that surface evaluator back, I can ask it, okay, what's the minimum value? And when we talk about the space in a surface space, rather than X and Y, it's usually referred to as U and V. So I have a U direction in one and then V in the other direction. So I can find out what's the minimum U value and maximum U value, and then minimum and maximum V values for that surface. So that's what this program is doing. So I'll select a face. It gets a surface evaluator. It asks, okay, what's the minimum value? What's the maximum value? And then it uses this density that I have on the dialog to, again, call that evaluator, and well, it creates an array of points that fall within those parameter space. So let's make it easy, and let's say I do have a surface that goes from 0 to 1, and then the density I've just set is 2. So I'm just going to divide up this space, so I end up with four boxes. So so I would have a point that's at 0, 0, a point that's at 0.50, and a point that's at 1, 0. So that would define a line along one edge, and then I would have a point that's at 0.5, another point at 0.5, and one at 1.5. And so I would define another line, and then finally 0, 1, 0.5, 1, and 1, 1. So there's these 9 points defined in this rectangular grid. So I got the minimum and maximum values, and then define these points, and then I pass that to this evaluator and say, okay, here's some 9 points in UV space.
Brian, are you showing the code?
No, I'm just kind of describing what it's doing. I think the code would be kind of confusing to talk about.
Okay, sorry.
Yeah, no problem. So here's 9 points, and then it gives me back the XYZ equivalent in model space. So the evaluator does that. So I'll change this to 2, and I'll pick this face. And it might be kind of hard to see. I have a hard time seeing it myself, but there it got those 9 points back. And then what I'm doing is, because we don't have custom graphics right now in the API, I'm drawing a sketch to show the results. So let me change this to, let's go back to 10. And so now you should be able to see a little better. So here's this grid displayed on the face. And even though it's kind of this weird shape, there's still a grid, right? And so I'm able to use this evaluator to do that. And let's see, let me pick, say another face. So here's a face on that other part, and it's divided up into this grid again. And so all faces really have, you can think of them as being rectangular. So I have that rectangular sheet of rubber, and so this parametric grid is always defined in this rectangular space, but it could just be really twisted around. But then what happens on something like this? This doesn't seem very rectangular. But then it really is. So the underlying surface is rectangular, but it's just been trimmed by curves that define some other shape. And then the other thing this little program does, let me pick this one, is instead of curves, I could also calculate normals. So then I get these little whiskers off of the surface. But so again, this is using that UV space, and then it's going from that, using the evaluator to go from UV space, the parameter space of the surface, to model space. And there's functions to go the other way too. Here, given a point in model space, give me the UV space point of that, the equivalent. So, all right. So let's, might be wondering, okay, so this seems kind of some crazy stuff. So why would I really use any of this? And so here's some examples of some things that you might do. And I mentioned in the other ones, the other presentations a couple of times, that when you're using the API, there are things that are very similar to using it through the user interface, but there's some other things that are very different too. And one of the things that's very different is it's hard to define geometry. And so, like in the user interface, if I want to create a box and then fill it an edge, a particular edge on that box, it's very easy to draw it, and then I know which edge, and I just say, okay, that edge. But now if I'm doing that through the API, how do I find that edge? And so I know in my mind there's some kind of criteria that defines that edge. And so I would draw the box, I get back the body, and now I would use these things that we've been looking at to be able to interrogate that body and find the edge that matches the criteria that I understand that edge has. So this isn't particularly easy. It's kind of like solving a puzzle, really. You have to figure out what are these criteria that I'm going to write code to figure out. So, and we'll look at one example here in a second where we can kind of talk through it. But this one I grabbed. So this was a question that was on the discussion group within the last couple of weeks. And so somebody has this part, which is basically a sheet metal part. And so they want to be able to have the user select an edge, which you see has pointed to there. And then he wants to find that other edge called the thickness edge, and then use that to create a construction plane that he's going to draw some additional geometry on. And so using this BREP stuff, so I should be able to figure this out. So given the selected edge, so now I have an edge, right? And from that edge, then I can query and find out what faces it's connected to. And so in this case, I get that top face and then that smaller, what he labeled there as thickness face. And so if I assume that the top face is probably going to be bigger than the other, then maybe I just look at the area of those two faces and get the one that has the smaller area, and then I assume that's the thickness face. And then I can get the edges from that face, and then I would get maybe the two edges that connect to the edge that's been selected. And so now I would get that, what he's labeled as thickness edge, and then I could use that to get some of the geometry that I need to create that construction plane. All right, here's another example. So this is using the 2D evaluator, and so what I have here, and I have a running sample of this. I might, in a second, I'll go ahead and run it, but I think because of the latency and over the web, it won't show much. But what this is I can select a curve, and then it flies the camera along that curve. And so what I need in this case is, given a sketch curve, I need to be able to find points along that curve. So from a curve, from a sketch curve or from an edge, I can get a curve evaluator, and so I can do those evaluations on the curve, and so I can find evenly spaced points along any curve regardless of what shape it is. Here's one that given, say, that part on the left, so given any part, I want to find holes inside that part, and then seal them up by putting a cork in each one. So how would I do that? And so again, that's using this BREP stuff and the evaluation stuff to do this. So one approach could be, okay, so I have the user pick a body, and then now I get all of the edges from that body, and I start looking through the edges, and I'm looking for any edges that are circles, that are full circles. But I need more than that, because these holes are represented by circular edges, but this boss is also a circular edge. So from that edge, then I get the faces that are connected to that edge. So in all of these cases here, I'm going to get a plane, and I'm going to get a cylinder. Okay, then I get a normal from that cylinder, and I see if the normal points away from the axis of the cylinder or towards the axis of the cylinder. So if the normal points towards the axis, then I know it's a hole. If it points away, then I know it's a boss. And so now I've found all the edges of holes, and then I could create these cork parts and insert them into that hole. So this stuff does have a real practical application. It takes a little bit of getting used to, and but it's pretty powerful, and you can do really automate some things that would be extremely tedious otherwise. So that's really what I had to cover today. I'm just curious how fast this will run, this animation one. Let's give it a try here. So I have this little add-in here. And so I can just pick a curve. And the up direction I know is plus Y. And this controls how fast I fly through. This I haven't implemented yet, this bank curves yet. And then I can say animate. And so now it flies through the model, and I don't know that you'll see hardly any of this on your side, but so it was smoothly flying through for me, and you're getting one every 200 or 300 frames. Right, so that's the end. But so that's capturing. That's just using that UV space of a curve and then using the API to reposition the camera along those points that I'm getting. All right, so let's go ahead and open it up to questions on this. What we talked about today, or any other topics are fine too. Yeah, so Marco asked if I can share the slides and the examples, and yes. So I think probably the best place maybe to share that is I'll post them on Mod the Machine blog. So if you're not familiar with that, if you you can do blogs.autodesk.com/mod MOD the machine, and it'll take you to that. So it's the kind of the manufacturing APIs blog, and each this stuff up and post it. A couple of the samples are really rough, so I need to clean them up a little bit. And Elmar, I've unmuted you if you had a question.
Oh yeah, hi. My question is about that. Says the surface geometry. You have the the NURB surfaces. Can you just explain more about that one?
Oh,
The second one is within that sort of surface geometry. You also have a cone, and can you actually create cone through API? Because you don't have the cone in your workspace when you try to create a solid object.
yeah. So so the first question, what's a NURB? So that stands for non-uniform rational B-spline, and so it's a mathematical way to define. Really, through a NURB, you can accurately define a plane, a cylinder, sphere. All those other types could be defined by a NURB, but typically where NURBs are used is for free-form kind of data. And yeah, I don't have any slides that really show what a NURB is explicitly, but
Can we do for next week? Like, because I think next week we have like 3 sessions which are like to be assigned. Can we add to the sessions?
yeah,
One of them.
potentially, yeah, we could talk about that a little bit. That's what I'm kind of guessing, is that maybe these next sessions won't be big topics, but maybe just several smaller topics that. And so this could be something we talk about in a little more detail. But it's when I have one of the places where it's used most often in Fusion is whenever you convert a T-spline back to a B-rep. When I leave the T-spline environment, those are all NURB surfaces that get created. And if I draw a spline in a sketch and I extrude or revolve or do something with that spline, the surface that's created is going to be a NURB in that case.
Okay.
And then the other question you said with the cone.
Yeah, the cone, because it's not available in one of the solids. It's just like a cube, and so but you have like a cone in surface geometry. So can you actually create the cone through API?
Well, yeah. So you don't. Well, none of the geometry, like I said, can you explicitly create through the API. You create it through features, right? But you can't create cones through features. So if I just draw a circle and do an extrude, I can give a draft angle to that extrude, so that will create a cone.
Okay.
Or I could draw a line that's at a slight angle to another line, and then revolve that around the line, and then that would result in a cone too. So there's a lot of ways I can end up with a cone, but there's just not a primitive command to create just a cone all by itself, right? I can still get that same thing by, like, say, doing an extrude or a revolve, but
Yeah.
but what we're talking about with this geometry, I should have been more explicit with this, is it doesn't matter how it was created, that we're just interrogating the shape of the result.
Okay.
Right, so if I have a box that I created using the box primitive, or I drew a rectangle and extruded it, when I query that, I don't know how it was created. I don't know that one was a primitive and one was an extrude. I just know, oh, here's a box, or here's a body that has 6 faces, and they're all perpendicular to each other, so it defines a box.
So the end result is still going to be solid. So even if you use the sketch it and then extrude, or just create like primitive, is that what you're saying?
Yeah, it's all the same in the end result.
Hmm.
So really the only reason you would choose one over the other is how do you want to parametrically control it? You know, if I want to edit it, be able to do something, maybe one's more convenient than the other. But as far as the API looking at the result, if I'm just looking at the BREP body by itself, there's no way for me to tell if it was created one way or the other. I'm just looking at the result. It could have been imported from a step file even, and I don't know. It's 6 faces, 6 planar faces.
Yeah. What I think is, like, just out of curiosity, the cork you showed, like, to plug the hole, are they actually get aligned, or they just fit the hole?
Can you say that again? I missed part of it.
You know that you have like the 3 holes in the solids, and then you to place the cork into these holes.
Yeah.
They get aligned, or how does that work? Like,
How does it figure out where to put?
That's the last one. Yeah, the last one.
How does it figure out where to put the cork?
Yeah, plus to get aligned.
Yeah, and so this one, I've written this program a couple of times in Inventor, and I just haven't had time to do it in Fusion. But what it will do, so like I said, that it interrogates it. So it ended up finding out those circular edges that represent holes.
Not go phase by phase, like checking every phase. Does it have sort of the what's called loophole?
Yeah, well, how I did it is I just got all of the edges. I didn't go face by face. I just got all of the edges in the part. And then I go through those edges, and for each edge I get the geometry. And then I check if that geometry is a circle or not. So now that had just eliminated all of the straight edges that I see.
Okay.
So now now I have just circular edges, but I want the edges that are on the holes. I don't want the edges that are on the boss. Right? I don't want to put a cork on the boss. So now I have to figure out, okay, what's different about the circular edge that's on a hole versus a circular edge that's on a boss. And the difference is that I'm using is the normal on that cylinder. The normal for a hole points. Remember, a normal always points out of the solid.
The anti-clockwise, sort of. They point different directions, is it right?
Yeah, that could work too. Actually, is that that CoEdge would be in a different direction for the internal. So that would be another way. Yeah, is that loop an internal edge or not? Although that doesn't totally work. So that works for the edge on the outside of the boss, but not the edge that's on where the boss connects into the body, because that would also be an internal edge. Right?
Okay. Did you do alignment at the end, or?
Yeah, and then so eventually I figured, so you doing that, doing and then getting normal from the cylinder, then I could figure out, okay, which edges do I want? So in this case, I got these 3 circular edges. And so
Yeah.
from each edge, then I can get the center of that edge
Mm-hmm.
and the normal of that plane. So now I really have all the information I need to insert to figure out the position of where that cork needs to go. So I know the size because I have that circle, and I have the center point and a normal along that, and then that's enough to figure out where the cork needs to go.
Okay, that's pretty cool. And then last question, actually, sorry. I was just playing with the JavaScript, and for some reason, like, I couldn't find like how to actually edit and run the JavaScript file Fusion. Could you just demonstrate like how to, like, I mean, I know how to create the file, but how to like edit it and then like run it so it will display it on the actual thing in Fusion.
Yeah. So there is one problem with doing that is it'll work the first time, but then if you make some additional edits and then try to run it again, you won't get the new version of your program. It won't be the updated version. It'll still run the old one, and that's a bug that the Apple has with their current WebKit, and they've recognized it as a problem, but it's not been fixed yet, and it's not really anything we can do to work around it. We're just relying on them to fix it at some point.
See.
So let's see. Let me just find a. So here's, I don't know what's in this one. I think this is just the basic script.
Yeah.
Oh no, so it's doing, well, yeah, nothing. Some stuff's commented, or yeah, it's commented out. So this, but it's a really simple JavaScript. So it brings up brackets for me to edit it in, right? And then so I could make some changes, save it, and then to run it, I can't do that from brackets. So that's one of the, I think, downsides of JavaScript is I use basically one IDE to edit it and then another IDE to debug it.
Okay. So what's the other IDE like you're using to debug it?
Yeah, so now I go back to add-ins. I pick that same script and then I can just say run and it will run, or I can say debug.
Okay, it's tricky.
Okay, so you see that debug? So I click debug, and so now I'm on Windows, so it starts up Chrome. Whoop. Not sure what happened there. Let me try that again. That was a little bit strange. Yeah, there we go. I don't know what happened the first time, but so it opens up Chrome. On your side, it would open up, I think, Safari.
Safari, yeah.
And then since I'm debugging, it automatically stops at this debugger statement. And now, at least here, I can add breakpoints and I can step through my code in here. And
yeah, the thing is, like, in JavaScript, I can like actually get the prompts. In Spider Python, I don't get anything. So I don't know what's the problem.
So prompts mean I'm not sure.
It's a bit convenient when you like kind of like learning things, like, and it's like you're clicking and then like things comes up and then you can actually find what you're looking for.
Oh, the code hints.
Yeah.
Yeah, I think something's broken there because we should have about the same kind of code hints in JavaScript as in Python, and then just the other day somebody noticed that we're not getting the code hints in JavaScript like we used to. So we're looking into that. I think something's broken in this latest release. But code
Yeah,
hints
so
should
like
be working in brackets. It should be about the same as you see in
and the
Spine.
brackets actually does work for me, like in the Mac, and but the Python doesn't.
Oh,
I don't
Python
get the
doesn't.
prompts. Yeah, Python doesn't.
Yeah, I don't know. I haven't tried it on Mac. It's working on Windows, but
Okay. Okay, got it. One thing is like on the Mac, when you do like a C++, it takes you to Xcode and then actually ask you for like a activation, so enable to access the development environment. Is that okay? Is that what you're supposed to do?
I think so. I think because of some security issues that Apple enforces, I think it asks you some extra questions.
Yeah, it says like provide the password and then like then so technically, so if I give the password, so it's basically it will connect the Xcode to the Fusion.
Yeah, I'm not sure. I don't use Mac hardly at all.
Are you planning to introduce another language, so like a Swift maybe? It just makes our lives easier.
Well, yeah, and there's no other plans. Unfortunately, I don't think there's any good multi-platform languages. They're really
All right.
that solve everything.
I think there's a problem now with the Python to get like an Xcode, because before like previous versions was alright. Now they upgraded to El Capitan, and so it's like got some glitches.
Huh.
And then yeah, so anyway, I probably gonna alternative is gonna be like C++ probably at the end
Yeah.
to be able to do stuff. Because the Xcode still supports C++, C, and Objective-C and Swift.
Yeah. Yeah. C++ is, I think for professional applications is definitely the best choice.
Yeah. Okay, thank you very much. Thank you for your quick answers.
Yep. You're welcome. All right. Any other questions? And let's see, I had that one slide here. Yeah, for the upcoming session. So this is the last one where we really had a well-defined topic. And so please feel free to email to Fusion Hackathon at Autodesk.com and let us know, other topics you'd like to hear about. It doesn't have to be big things. We can cover, several smaller things, and it's okay if the whole session would just take a few minutes. So, but so I'll be thinking of some things, and I'd really like to hear what you'd like to see covered coming up. All right. Well, if there's no more questions, I think we'll call it good. So thank you for attending, and we'll have the Q&A session tomorrow and on Monday at 9:30 a.m. Pacific time, and then next Tuesday is this next kind of session like this. So all right, well, talk to you later, and bye.